Yours.
Okay, Muhammad, if you can share, I don't think it's on yet. Yes, perfect. Yeah, everybody, thanks for coming. Today we're very happy to have Muhammed Sayin from Bilkent University, Department of Electrical Engineering. Present his work on multi-team reinforcement learning. Please, Muhammed, you have 60 minutes-ish, more or less. Take it away.
Hello, everyone. Thank you for the invitation. And I believe that this seminar series is very timely because AI is getting more prevalent and we have multiple decision makers more than before. And today I will mainly talking about learning to coordinate and compete in a dynamic environment. When we think about life is not one-to-one. For example, if you look at the world politics, the major two wars in the last century, World War I and World War II, were between two groups or teams of states. Furthermore, even now today, we can see that states are teaming together, such as NATO and BRICS, in terms of political or economical reasons. Furthermore, in the business side, some businesses are forming some alliances. Look at airlines. For example, there are three major ones. Star Alliance is one of them, and Turkish Airlines or United Airlines is a member of this. Even though those are individual companies, individual businesses, they form some alliances. On the other hand, in the automotive manufacturers, we also see some alliances, even across world. For example, Stellantis includes companies such as Fiat or brands such as Fiat, Alfa Romeo, Citroën, or on the other hand, we also know there is this team of brands, Renault, Nissan, Mitsubishi, and goes on. And furthermore, in the security side, when we try to secure our system, we generally divide our team into two parts, blue team and red team. Red team tries to infiltrate into the system, while blue team tries to protect or prevent the intrusion. And this is not just for network security or computer security. Even for the security of infrastructure, there is not a single threat. There are multiple threats, and they have some aligned objective. What is the aligned objective? The aligned objective is being an adversary. Even though they do not form a team, their aligned objective somehow can push them towards forming a team. And finally, with the prevalence of AI and robotics, we will start to see more and more such systems in our daily life. And they will also start to form teams. Therefore, an important critical question for us, how can we predict the outcome of interactions in such multi-team settings? Can we apply Nash equilibrium, right? This is the fundamental concept for analyzing how human behaves in multi-agent systems. But the issue is, Nash equilibrium does not take team formation into account. On the other hand, maybe we can extend this to Team-Nash equilibrium, where teams act like a single decision maker, right? The next question is it justified? How predictive that kind of equilibrium for the practical settings? For example, for Nash equilibrium, maybe this is the main concept of this seminar series as well, finding some justification for this. Because there's a common belief that if we have some learning agents, even though they are not looking for some equilibrium, if they interact continuously and receive feedback from the environment, eventually they will reach an equilibrium. And learning in games literature specifically focus on this problem. Observing that, I want to ask this question. Can non-equilibrium adaptation of teams of learning agents reach Team-Nash equilibrium? Right? This is the main research question I would like to address today. Okay, let's look at the literature, what is happening, because this is a very big literature. I will try to present them in a systematic way. For example, I created this spectrum of games in terms of the alignment of the objectives. For example, we have the misaligned objectives. From the left to the right, it is misaligned to the aligned objective. At the either edge, we have zero-sum games where everyone has fully misaligned objective. On the right side, we have the potential games or identical interest game where everyone has an aligned objective. And at the either edge of this game spectrum, there's a bunch of results, right? And they are all well established, starting from the convergence of the fictitious play in both zero-sum and potential games, and many other results. And I'm particularly interested in this one because when we talk about zero-sum games, two-agent setting, there might be multiple equilibria, but all of them will lead to the same game value. On the other hand, for the potential games, when there exist multiple equilibria, they will not necessarily lead to the same potential function value. And the question is, can we be selective about which equilibrium we are going to converge? And there are some behavioral models, such as log linear learning, that can converge to optimal equilibria in potential games, and the optimality will be with respect to the underlying potential function. Yeah, it will lead to the maximizer of the potential function. And very recently, Markov games, which is also known as stochastic games, have been very, very popular since it is used as an ideal model for multi-agent reinforcement learning, and multi-agent reinforcement learning is the foundation of many AI breakthroughs. Although the Markov games or stochastic games have been introduced around half a century ago by Shapley, 1953. And recently, David Leslie showed that a slight generalization of best response dynamics, when you combine this with value iteration, it can converge to equilibrium in zero-sum Markov games, zero-sum stochastic games. And following that, we also show that a natural extension of fictitious play, where we combine fictitious play with Q-learning, can also converge to an equilibrium, even when agents don't know the model of the environment. On the other hand, at the potential side, there is Arslan and Yüksel 2017, where they address the convergence to equilibrium in team problems in a more general setting, where the underlying game is something like a weakly acyclic game. Leonardo's introduced the Markov potential game and presented that gradient-based methods can also converge to equilibrium in that setting. Baldwin and Laraki extended Leslie's framework and our contribution on fictitious play to the identical interest stochastic games. And later, we also showed that the same algorithm converging to zero-sum game can also converge to equilibrium in identical interest Markov games. And very recently, we also extended that log linear learning, which can converge selectively the optimal equilibrium in potential games to the Markov game setting, Markov team problems. And today, I will also present this work with Sayin. Okay, this is the two ends of the spectrum. We have extensive results. What about in between, right? Where agents have partially misaligned objective or partially aligned objective. Unfortunately, there are some negative results. Firstly, let's start with Shapley. Shapley presented a game in which fictitious play will not converge to equilibrium back in the 1964. And there are some impossibility results by Hart and Mescal showing that there exists no uncoupled learning dynamics, which does not take into account the opponent's objective and still converge to an equilibrium in every class of games. Right? It is not possible. There is no universal guarantee. Observing that, people started to relax the equilibrium definition. For example, look at the correlated equilibrium, convergence to correlated equilibrium, and many others. Or relax the convergence guarantee, right? Rather than a strong sense of convergence, maybe we can look for a weaker sense of convergence, and goes on. On the other hand, multi-team problems is at the in between these two extremes. Why? Because agents have an aligned objective with other team members, but they have misaligned objective with the opposite teams. Therefore, we are in the center. Thankfully, the special structure of this problem, where we blend cooperation and competition together, can still lead to some refined results where we can have strong convergence guarantees for fictitious play or best response type of dynamics. While there are many results, like in the multi-agent learning setting, even though I only selectively pick several of them, this is a very big literature. And if you go to the computational side, some algorithmic approaches, the literature is even larger than that. But on the multi-team side, the literature is very limited. Indeed, it started to get attention very recently, starting by Sally and Cathy in 2018. And if you look at all those papers, they have this common theme. They have two competing teams only. Sometimes team has a single member, one versus many. And their main goal is the effective computation of equilibrium rather than showing the convergence of best response type of dynamics. Furthermore, they establish communication or they impose coordination by using communication, either beforehand, ex-ante communication, or online by exchanging some information, such as their gradient information or their estimates, things like this. But this is not a coincidence because this is a challenging problem. There are multiple challenges. For example, team members need to learn the efficient coordination with adapting team members, right? They need to adapt to the other team members while not only coordinating in some action, they need to coordinate in the optimal action. While they do that, the optimal action for the team will change because optimal action of the team will depend on how the other teams play. But the other teams are also learning, they are adapting their actions. In the meantime, the underlying environment, when we focus on Markov game, it is also evolving. They need to solve some dynamic program to be able to get their best response, get their true best response rather than myopic best response. That can also take into account the continuation payoff. In other words, future interactions. Those are the challenges. But when we think all those challenges in isolation, in other words, separately, there exists some well-established results. For example, let's focus on the first one, learning efficient coordination with adapting team members. If there's only a single team, the underlying environment is stationary. In other words, they are playing a game repeatedly. In that case, as I mentioned, log linear learning will reach the optimal equilibrium in potential games. On the other hand, let's look at the second one. If we have multiple agents, in other words, each team has a single member, and the underlying environment is stationary, then fictitious play will converge to equilibrium in zero-sum and potential game settings. And finally, if you have a single agent and the underlying environment Markovian, in other words, we have a Markov decision process, even when we don't know the model, Q-learning can converge to the solution. Therefore, our key idea is combine all those separate and well-established classical results together to address this problem. But when we do that, we will use timescale separation from the fastest to the slowest, from the top to the bottom. And the main reason is this. Team members update their choices more dynamically, and therefore, right, this is our point of view. Therefore, recent actions of our team members are more important for us. On the other hand, let's look at the bottom line. Our preferences, in other words, the values of states, will evolve less dynamically. Therefore, we will put more emphasis to the past rather than the recent observation. That means that we will use larger step size for the actions of, for learning the actions of our team members, and smaller step size for learning or solving the underlying dynamic program. And fictitious play or learning the opponent's actions will be in between them. And when we do that, we will have this kind of stages. At the top stage, where we have the fastest time scale, agents will follow something like a log linear learning, as if the opponent teams play according to some quasi-stationary strategy, not exactly stationary, but quasi-stationary thanks to the time scale separation. Furthermore, the environment will be something like a quasi-stationary. When they do that, thanks to the log linear learning, they will reach to the optimal equilibrium. Yeah? When they reach to that or track the optimal equilibrium for that quasi-stationary cases, their behavior mimicked a single decision maker behavior. In this case, the problem will reduce to something like a fictitious play, where team coordinates in the best team response. And thanks to the time scale separation, still the underlying environment will be something like a quasi-stationary environment. And in this case, fictitious play can reach an equilibrium, given that fictitious play reaches an equilibrium. Now in the Q learning part, we can solve this dynamic program problem, at least in the zero-sum setting, thanks to the contraction property of the Shapley iteration, Shapley operator. Right, this is the main idea. Combining them all together, we have this triangle. At top, we have the log linear learning to address the team problem. On right, we have the fictitious play to address the competition with other teams, and Q learning to solve the dynamic program. Combining log linear and fictitious play, recently we presented Team-Fictitious play, where we have multiple teams but stationary environment. Combining log linear learning and Q learning, we presented logit-Q dynamics, where we have a single team but a Markov game. And lastly, combining Q learning and fictitious play, we presented that 2x scale fictitious play extension, where we have multiple agents and Markov games. And multi-team reinforcement learning is at the center, unifying all those algorithms together. To be able to present this, I will build starting from the Team-Fictitious play. And this is a paper with my graduate students, Ahmet, Sait Dönmez, and Yüksel Arslantaş. They are also in the audience. And this is the multi-team games framework. We have finitely many teams. Each team has finitely many agents, and each agent has finitely many actions. They may even have some network interconnections, as you can see on the right. We have blue team with 3 members, orange team with 3 members, and green team with 3 members. And arrows, directed arrows, show the interaction, meaning that their action can have an impact on their payoff. And we will specifically focus on zero-sum potential team games. What is that? I am assuming that teams have an aligned objective, which is quantified by the team potential function, right? They do not necessarily have identical objectives. They have aligned objective quantified by the captured by the team potential function. For example, team M has phi M as a potential function. This potential function means this: agent's individual objective or individual payoff, denoted by U, is aligned with the team potential in the sense that if other team members and other teams play a fixed action, only that agent changes the action. In that case, the change in the agent payoff will be exactly the same with the change in the team potential function. Right? Just like the ordinary potential function for a single team if there were no other team. And this is a zero-sum game in the sense that if you add the team potential of every team, it will sum to 0. Unfortunately, we will not be able to present a good result for the multi-team case. Why? Because even though the underlying game is zero-sum, when we have more than 2 competing team or agents, it will no longer have the peculiar properties of 2 agent zero-sum game. For example, you can present any general sum game as a multi-agent zero-sum game by adding some auxiliary player with a singleton action, and its payoff will be the negative of the sum of the other agents' payoff. And that implies that we don't have any we don't have a elegant result specific to that case. Thankfully, under certain structures, this is still possible. One of them is the polymetrics games. In the polymetrics games, we have pairwise interactions, and the total payoff will be the sum of those pairwise payoffs. For example, on the right, you can see that. And these agents' teams are collected together as if they are a single agent. In that case, their team potential is phi 1, for example, for team 1. And that phi 1 consists of 2 additive terms, phi 1, 2 and phi 1, 3. Phi 1, 2 includes the actions of team 1 and team 2. Phi 1, 3 includes the actions of team 1 and team 3. And we have network separability. Once we have such pairwise separability, we still have some elegant results. And one example is this. Imagine that we have two teams, and each agent has some local payoff, Ri. Agent I's, the one pointed out in red, has the total payoff, which is the sum of neighboring team members' local payoff, subtracted by the neighboring other teams members' local payoff. If that is the case, team potential function is given by this, where we subtract the other team's sum of local payoffs from this team's sum of local payoffs. From this, you can also see that this is a zero-sum game because the other team will have exactly the opposite of that. And this is one of the examples to construct such multi-team zero-sum potential team game. And for such cases, rather than looking to the Nash equilibrium, we will look at the Team-Nash equilibrium, where team is like a single decision maker. This is a generalization of team minimax equilibrium for two team cases to multi-team cases. And here we will represent the joint strategy of team M by pi bar M. Bar refers to the team. And here the agent strategies are not necessarily independent. There can be some correlation between them.
Muhammad,
Yes.
just a quick intuition question. So for this extension, for this network separable team zero-sum game, is the main difference to a general, like if there were no network separability, is the main difference to that multiple teams have no incentive to join together, form a bigger team, and thereby destroy some opponent, because basically their joint effect is not enhanced by jointly doing something. It's just basically the same as if they were separately doing whatever they're doing. Is that
Okay, I haven't thought about that. Indeed, in our setting, we will assume that teams are fixed. They are not forming coalitions. And I think the main intuition why polymetrics games work, looking at their convergence analysis, basically reducing everything to pairwise interaction and then adding them together creates some linearity. In that cases, it will be very similar to some zero-sum games played in parallel, with weak coupling, where you need to use the same action in all of them, right? Yeah, this is my understanding of why it works, but that it would be interesting to observe this from a team formation perspective. Yeah, I have never thought about that.
okay?
Yeah, but that's a good question. Right? That can be interesting research direction. Any other question? Yeah, perfect. Okay. As I said, the agent strategies are not necessarily independent. They can be correlated within team. The joint team's strategy will be within the joint strategy space of every action, not necessarily the product space. In that case, we will define the Team-Nash gap like this, as if each team is a single decision maker, and look at whether this Team-Nash gap converges to zero for our algorithm or not. As I highlighted before, this is exactly like a Nash gap, where teams are like a single decision maker. Okay, we presented this Team-Fictitious play, which combines log linear learning and smoothed fictitious play. And let's remember, what is log linear learning? Log linear learning reaches the near optimal equilibrium in potential games. On the other hand, smoothed fictitious play near equilibrium in zero-sum polymetrics games. That's a good property of polymetrics, zero-sum polymetrics games. Fictitious play will also converge to equilibrium there. Okay, what is the difference between them? The difference is in the log linear learning, agents update their action with some friction, meaning they will not update their actions all the time. They will do this occasionally with some randomness. For example, they can do this independently with some probability, or they can do this in a coordinated way, such that only one agent will update its action. On the other hand, in the smoothed fictitious play, there will always be an action update, right? There is no friction. In the log linear learning, when they update, they will soft respond or smooth, they will take a smoothed path response to the other's latest action, right? You can think that they form a belief about the other's action strategy, but they will think that the others will play the latest action. Right? Or you can say that they have a short memory. They put more weight to the recent observation. On the other hand, in the smoothed fictitious play, agents form a belief about the other agents. Looking at the entire play, they might even take the empirical average of the actions played in the past, and they take the smoothed best response or the best response to that one. There is a lot of alignment between log linear learning and smoothed fictitious play. And the key difference is log linear learning gives more importance to recent actions. Fictitious play gives more importance or less importance to the recent actions. And this somehow inherently creates a 2-time scale dynamic. And this is the algorithm we present. This is the log linear learning plus smoothed fictitious play. The belief update is exactly like the fictitious play. Now they form a belief about the other team's joint strategy. And when they do that, they can use some decaying step size, or they can, this step size can be even 1/t, such that the belief will correspond to the empirical average. In the log linear part, there is no iteration. It will only respond to the latest action of the team members and the belief of the other team's strategy. Right? In that case, there is also a friction, right? With certain probability, they will do the smoothed best response or they will continue to play the previous action. And when we have this kind of simple dynamic, a natural combination of log linear learning and fictitious play, the empirical average of the joint team actions converges to near Team-Nash Equilibrium, almost surely. Here we have near. Why? Because they are using smoothed best response, meaning there is some, this is not the best response, and this leads to some error. And because of that error, you can think this one as some exploration error. They are not exactly converging to the Team-Nash Equilibrium. On the other hand, we can consider that smoothed best response as some best response to some perturbed game objective, where the perturbation is exactly the entropy regularization, and the corresponding equilibrium concept will be quantum response equilibrium. And if we extend this to the team setting where teams act like a single agent, in that case, empirical average will converge to the exact team query. And what does that mean? That means this. In the long run, teams play the Team-Nash Equilibrium with high frequency. And this is a sketch of the proof. On the left-hand side, you can see the details of the algorithm. But I would like to visualize that algorithm in this diagram. Right? We imagine that we have two teams for simplicity. And there is two updates. One is the belief update, which takes the previous belief as an input and the action of the opponent team as an input and produces the next belief. On the other hand, the action update takes the previous actions of team members and the belief for the opponent team and produces the next team action. But in that case, thanks to the structure of the smoothed best response, we can view this update structure as if there exists some underlying transition kernel which maps the previous action to the next action, while that transition kernel depends on the belief. If that is the case, agents' actions form something like a Markov chain. But the issue is that Markov chain is non-homogeneous. Why? Because the transition kernel, depending on the belief, will change in time. This is the challenge. To resolve this challenge, we made this observation. Even though the transition kernel depends on the belief update depends also on the step size alpha t. And the good thing is alpha t decays to 0 in time. Thanks to that, the changes in the transition kernel will get smaller and smaller. Observing that, we divided the horizon into time windows. We call them epochs. Within the epochs, the evolution of the update for the beliefs and team actions will look something like that. And we will approximate this with a reference scenario where we stopped updating pi at the beginning of the epoch. When this is the case, the action profiles of teams form exactly a homogeneous Markov chain. And this is not in it, this is a special Markov chain. This will be exactly the Markov chain formed by the action profiles in the log linear learning. One good thing about this is this. In the log linear learning, the action profiles have a well-established or well-characterized stationary distribution. We even have a closed form expression for that. And another good thing is, in a stationary distribution, the most frequently played action profile will be the maximizer of the potential function. The next question is, will this reference scenario a good approximation for the actual scenario? And thanks to that decaying step size, we can see that within that epoch, if the epoch number is large, sufficiently large, we will have something like a quasi-stationarity. In other words, the pi does not change much. If that is the case, transition kernel does not change much. Furthermore, since this is the case thanks to the smoothed best response as well, right? Because smoothed best response has some Lipschitz continuity cases. If the beliefs are not changing much, thanks to the Lipschitz continuity of that transition kernel will not change much as well. Thanks to that, we can establish a coupling between the actual scenario and reference scenario. And using that coupling, we can further show that the approximation error in between these two will decay to 0. If this decays to 0, in that case, team is coordinating in the best team response, then everything reduces to the smoothed fictitious play. Therefore, we can use the well-established results for the convergence of smoothed fictitious play for potential zero-sum games by using some Lyapunov function arguments, and convergence gets completed by that. This is the main intuition for our proof. And I would like to provide some illustrative examples as well, right? What is the impact of using coordination via log linear learning? For example, imagine that we have two teams and each team has 4 members. I am talking about the left figure. Each team has 4 members. If 4 members uses log linear learning for coordination, in that case, their convergence, the decay of the Team-Nash gap will look something like this blue one, the top curve. On the other hand, if we group 2 of them together, right, as if they are a single agent, follow the Team-Fictitious play, in that case, we have the orange curve, which is relatively faster. Finally, we group all of them together. Somehow we establish some dictated coordination between them, centralized coordination. We have that green curve. And green is the fastest as we expected, but the performance does not decay much. In the middle figure, we compare Team-Fictitious play with other dynamics, such as smoothed fictitious play, where agents do not form a team, they act autonomously, individually. Furthermore, multiplicative weight update. In both cases, that can converge to equilibrium, but even though it can converge to an equilibrium, it will not minimize the Team-Nash gap. Why? And it is reasonable, right? Because agents are not forming a team. They are not trying to coordinate with team members. Therefore, the team objective does not necessarily go to the best solution. And there's this gap. And lastly, on the right-hand side, we consider a larger scale problem where we have 3 teams and each team has 9 members, and in total we have 27 of them. Thanks to that networked interconnections, we can also show that Team-Nash gap converges just the case very, very fast compared to the small scale examples. Right? If you have network connections, still Team-Nash equilibrium is a good prediction for the interaction between teams. Right? This also strengthens the predictive power of Team-Nash equilibrium for real-life team environments, multi-team environments. Also, recently we extended that to the potential game settings. Right? We have multiple teams and teams have aligned objective. Right? Rather than all trying to use some log linear learning type of algorithm, they will form small teams and such that they will coordinate within small teams and still respond or compete with other teams. In that case, we can show that Team FP always converges. Furthermore, team formations can improve the worst case equilibrium guarantee as well. And yeah, also in terms of computational scalability, this will provide more scalable solution for that kind of problems. Okay, next, logit-Q dynamic, where we combine log linear learning and Q learning to address single team Markov game problems for optimal equilibrium convergence. This is also a joint work with my graduate student Ahmet Said and our undergrad student Onur Önlü. Now he moved to the Cornell University for PhD. Okay, what is Markov games, also known as stochastic games? Originally introduced by Lloyd Shapley back in the 1953. Here we have a dynamic environment with multiple states, and I am assuming that there are finitely many states, and there are finitely many agents. Each agent can take finitely many actions. And at each, they are playing this game over an infinite horizon, discrete time. K0, K1, K2 goes like this. At each time instant, they observe the state. They take their actions simultaneously. Their joint actions will determine their rewards. Furthermore, their joint actions and state will determine the next state by this transition kernel. We have some Markov property here. And their goal is to maximize the discounted sum of the rewards collected over infinite horizon with the discount factor gamma, which takes a value less than 1. In this case, we will focus on the joint strategy where the agents might have some coupling, in other words, some correlation in their actions taken. In that case, given the joint strategy, team member utility will be given by UI, depending on its local reward. Team utility will depend on some R function for the team reward function. And a special case is the Markov team problem or identical interest Markov games where everyone has the same reward. For such case, we will focus on the optimal equilibria. Since there exists some correlation between the agents' actions, this is not exactly Nash. This will be something like a coarse correlated equilibrium where you can, by changing your actions, you will not be able to improve it while there is a correlation between agents' actions. And we will define the efficiency with respect to the team utility, that U without I index. Okay, to address this problem, we will first generate the Bellman equation. This is the long-run objective, starting from time 0 to infinity, and the rewards are discounted by gamma. Imagine that our first state is S, and this K index is the stage index, time index. I explicitly incorporated that initial state in the utility definition. Now I can separate that summation into 2 parts. We have the first term rewards plus the continuation part based on the next state. We use total probability theorem to do that. And the good thing here is this. This boxed term highlighted in red is essentially the same with that utility if the initial state was S prime. The reason is we are focusing on Markov joint strategies. Environment is Markov. Actions are drawn according to Markov strategy. Therefore, everything is, we have some symmetry, and a time shift by 1 will not change the total reward. And in that case, if I define the value of that state with some other notation, let's say that V, and we will obtain the Bellman equation, which will depend on the joint strategy pi bar. In that Bellman equation, I will denote or define the circled term as the Q function, specific to the joint strategy. Observing that the value of the Q function has two components. One is the immediate reward, the other one is the continuation payoff. And in that case, even though the underlying game is played over an infinite horizon, we can view the interaction between the agents as if they are playing some stage game, but the stage game payoff will not be the immediate payoff. The stage game payoff will be the Q function corresponding to their joint strategy. In this case, we can analyze the classical repeated play results and apply them to this setting within the stage game framework. Okay, to be able to do that, specifically for the optimal equilibrium learning, we will combine log linear learning and Q learning. Remember the log linear learning, it can reach the optimal equilibrium in potential games, and there exists some friction, and it will always respond to the last action of the team members, and we have some recency. On the other hand, Q learning can solve this Bellman equation, even when we don't know the model, but it will be able to do that in a single agent setting, right? In a centralized way. And when we don't know the model, it will be able to solve this by sampling the next state to approximate the continuation payoff. Since look at this Bellman equation, right? When we don't know the transition probabilities, we will not be able to compute that expected continuation payoff, but we will use the payoff for the next state as an approximation for that. But that will create some sampling error. To address that sampling error, Q learning uses some decaying step size. But thanks to the decaying step size, we naturally have a 2-time scale dynamic, right? We are not artificially imposing a 2-time scale dynamic. As in the Team-Fictitious play, we naturally have a 2-time scale dynamic here. And the update rule will look like this. It will be exactly like the Team-Fictitious, it will be exactly like the Q-learning algorithm. But the difference will be how we take the actions. How we do the action update will be coming from the log linear part. And furthermore, we will compute the values by looking at the most frequently played joint action, right? If you do that, that will be like, since they will be most frequently playing the best team response, it will be like maximizing the Q function, right? Even you might ask why they don't do this immediately. The issue is they have their local Q estimate, like Qi and reward I. For the Markov team setting, this will be the case. They can do this joint optimization, but when they have local rewards, they will not be able to do that because they don't know the reward or Q function of the other players. And frankly, there are not many cases where this will work. But in the paper, we have shown that if the state transitions are controlled by a single agent, then this can play an important role. In it, this is one of the interesting property of Markov potential games, or the generalization of stage payoffs with potential property to the Markov game settings. Unfortunately, because of that continuation payoff part, we will no longer have a potential game in the stage games, right? This is a significant challenge. Okay, and when they do the update, they will use a step size depending on the number of realization of the corresponding state action pair, and this will lead to some asynchronous update of the entries of Q function. Why? Because we are only updating the terms for which we observe the reward. In other words, we are updating the ones only for the current action. and this will lead to some asynchronous challenges, but this kind of challenges have been addressed back in the days in 90s, thanks to the John Tesla. Okay, this is the informal result. If we have an irreducible Markov team, why we focus on irreducibility? This is because we want agents to play the stage game associated with every state infinitely often, so that they will reach an equilibrium. If they don't play that stage game sufficiently many, in that case, they will not be able to reach that equilibrium, and this is an issue for the optimal equilibrium performance. If we have some irreducible Markov teams, in that case, the joint strategy and Q function estimates converge respectively to the optimal equilibrium and the corresponding Q function almost surely. And this implies that under such mild assumptions in terms of irreducibility, the team plays the optimal joint actions with high frequency. And what are the key challenges? The key challenge is that asynchronous update. For the single agent case, it has been addressed, but when we incorporate that local linear learning, we still have that challenge. Auxiliary stage games get played only when the associated state gets visited, and this will lead to some asynchronous updates of the parameters for different states. Even though we have multiple state dynamics, they are all coupled. We need to consider all of them together. And our key idea is, again, we'll use some visualization. Imagine that we have 4 state action pairs, S bar and S states, and A bar and AB for S bar state, and A and B is for the state S. The state action pairs for state S are highlighted with red. And the x-axis, the horizontal axis is the time, discrete time. Now imagine that we have the global trajectory of state action pairs, and you can see observe the transitions on the diagram as well across those states. Given that global trajectory, we will focus on the local trajectory. Local trajectory of the corresponding state S, like we fix some state S and focusing on the local trajectory of the actions played specifically for that state. In that case, the local trajectory will be from SA to SB, then back to SA at time k+1. Also, we will keep track of time with respect to the visits to that state. But the global time will be different. And to establish the connection between them, we will introduce 2 parameters. One is W, the other one is the Z. W will be corresponding to action, local action for that state. Z will be the actions, state action trajectory outside that state. For example, this ZK-1 will correspond to first transitions, first the pair S bar A bar, then the pair S bar B bar. Now we will consider these 2 parameters together and look at their evolution. When we look at their evolution, we observe this. Since the Q function, by the update of its nature, it will depend on the trajectory of the state actions realized up to time Tk, the actual time, right? K is the time index for the local time. The corresponding time will be denoted by Tk, the global time. Now, since our parameter pair, auxiliary parameter pairs, W and Z already includes that state action trajectories, we can also say that Q function is sigma measurable with that pair's previous trajectory. And given that we observe this, there exists some underlying transition kernel over the countable space of those WZ pairs, and it will depend only on the history of those their trajectories. And now all we need to do is approximate that thanks to the decaying step size of Q function. And again, we will divide the horizon into epochs. But now the epochs will be depending on number of visits to the corresponding state rather than the global time. And now within that epochs, we will approximate that transition kernel with some homogeneous Markov chain, as we have done for the Team-Fictitious play. And thanks to this structure, that homogeneous Markov chain will be exactly the one for log linear learning. We have a closed form expression for the stationary distribution. Once we couple their evolution, thanks to the decaying size, the coupling error, the approximation error will decay to 0. Thanks to that, now we can say that joint actions specific to each state can track to the stationary distribution of log linear learning. Since we use the most frequently played joint action, this will mimic the ordinary Q learning update. And this completes the proof. This is the main sketch of the proof. Even though there are many, many details, we should be careful, but the key ideas are those. And I want to present some illustrative examples. Here you can see that how the gap, equilibrium gap, decays to 0. Right? I only presented that exploration-free case where we use the most frequently played action. On the other hand, rather than the most frequently played action, if you take just the empirical average, there will be some error due to the exploration, and the error will depend on temperature parameter we use for the smoothed response, but still the convergence behavior will be like this. You can also see that how the Q function estimates converge to that unique underlying Q function for the best team response. Okay. And lastly, we combine this Q learning and fictitious play together. But I do not want to present the details of this work because we have a collection of work and I do not want to give further technical details. And instead, I will try to explain how they address different aspects. For example, our work on fictitious play combined with Q learning can converge the equilibrium in zero-sum Markov games. And a challenge was the stage games were not necessarily exactly zero-sum, even though the underlying game was zero-sum. And we addressed this issue by using some new Lyapunov function formulation and show that stage games become zero-sum asymptotically, and we can prove convergence. And our joint work with Leslie on decentralized Q learning addressed this problem for the payoff-based dynamics, where we extend the individual Q learning to Markov game settings. We further show that it will also converge in Markov team problems. And recently, we try to address the robustness of these algorithms to heterogeneities. Imagine that we have multiple agents, but they do not necessarily use exactly the same parameters. Our convergence analysis or convergence guarantees, are they still robust and will they still reach an equilibrium? And thankfully, the answer is yes. It will still converge to an equilibrium even under such parametric heterogeneities. And finally, we combine all them together, multi-team reinforcement learning. What is multi-team reinforcement learning? It will be solving multi-team games problem. We will have multiple teams, such as 2 teams, illustrated here. Each team will observe the global state, will take a joint action. Their joint actions will determine their rewards and the transition to the next state. If that is the case, we will combine log linear learning, fictitious play, and Q learning all together. Rather than presenting the exact algorithm, I would like to point out the update state. The action update state will be exactly like the log linear learning. The difference from the Team-Fictitious play will be, now we will have a Q function rather than a fixed fixed payoff, right? You need to learn the payoff of the stage game. And to learn the payoff of the stage game, they will use the Q update. And in the Q update, as in the logit-Q dynamics, they will use an expected value over the joint strategy profile across teams rather than taking the most frequent one. such that this will correspond to the equilibrium play. Furthermore, the step size for the belief update will decay with the number of visits to the corresponding state. And now we will have an imposed two-time scale dynamic where the Q update uses step size beta, belief update uses step size alpha, and beta goes to 0 faster than alpha, such that the changes in Q will be smaller compared to the changes in pi. If that is the case, this is an informal result, we can show that this type of two-time scale dynamics and under irreducible Markov team game assumption, beliefs and Q functions can converge to the corresponding near team min-max equilibrium and the corresponding Q function almost surely. And this is an illustrative example showing that. And here we have two teams. Each team has two agents, and there are 3 states, and each agent has 3 actions. If it is the case, after around 100,000 iterations, it will be near equilibrium, Team-Nash equilibrium. And depending on the exploration parameter or temperature parameter, the convergence error or the approximation error for the equilibrium will be smaller, proportional to that tau parameter. Okay, what are the key takeaways? Here, I presented some convergence guarantees for class of games beyond zero-sum and potential games. And we essentially use 3 classic algorithms, very simple ones: log linear learning, FP, fictitious play, and Q learning. And multi-team reinforcement learning combines all of them together. And their convergence guarantees shows that Team-Nash equilibrium can be a good predictor for multi-team environments, right? Even though there are, this is important because we will generally have non-cooperative agents forming some team. The question is, are they still going to be acting like a single decision maker, right? For businesses, it makes sense. On the other hand, imagine some security problem. You are trying to secure your system against multiple threats. Even though they are non-cooperative, they do not coordinate with each other. They have an aligned objective. The next question is, should we consider the worst case, such that all the adversaries are controlled centrally? And based on this observation, I should say that we should consider the worst case, because it is possible that they can learn to coordinate even in such dynamic environment, even in such adaptive environment where the defender and attacker adapt their strategies. And finally, this is also another observation, and maybe this is one of the fundamental reasons why all of those works. Here we use those classical algorithms, which are meant to model how humans play in life or in games. And they are rough models, rough behavioral models. And apparently those rough models are robust to perturbations, such as quasi-stationarity. And thanks to that, when you combine them by using timescale separations, they will still do the tracking for you. And moving forward, I am particularly interested in team formations, how agents can learn how to form teaming with others. And finally, I'm interested in forming a bridge between cooperative and non-cooperative Markov games from a learning perspective. And all the related materials are available in our website. And if you have further questions, you can always reach me via the email.
Thank you, Mohammed. Very, very interesting talk.
Thank you.
Let's open the space for questions. Please go ahead. I can start with questions if there's no other questions yet. So I wasn't so familiar with log linear learning, but it seems so it's correct that you need to observe all your team's previous actions in that learning scheme, right?
Not necessarily. In our algorithms, yes. There are also some payoff-based extensions of log linear learning.
Okay, okay. So all of this can be robustified to only making observations about your own payoffs, potentially?
Think that is a challenge, right? Somehow you need to distinguish a team member and opponent team member, right? If you only observe your team, your own payoff, it will be a challenge. But it can be extended to the case where you only observe your team members' action while not observing opponent teams. Maybe that kind of extension can be possible, but just depending on payoff, I think that will be a challenge.
I see, I see. Because I was wondering that, yeah, in the example of adversaries that can't communicate with each other and live on, you know, they just work on a computer that is completely separate, then it would be interesting to find a way, you know, where there's as little information as possible about your potential team members, and you can still achieve this kind of
Yeah, that's interesting.
problematic team building behavior. But yeah, I see. Yeah, maybe you can, I mean, it seems like maybe you can form some kind of you know, continuous extension from the I observe exactly who my team members are to I have a fuzzy idea of what they are or who they are, and then maybe I can form an estimate.
Oh, okay, some herding argument, right? Yeah.
Maybe this is yeah, I'm just wondering how to yeah, how to get this to this to a realistic model of maybe cybersecurity threats of um, self-interested agents
Yeah.
that are
I
that don't
also
know
like to
exactly anything.
highlight this. It is very slow, right? Compared to exact coordination. In the practice, it will take
Yeah.
quite a time to track that, especially if you have a large scale. Yeah, it will take some time.
That makes sense. Yeah. Yeah, I guess that's why teams try to practice offline before they interact with other teams. Makes sense. Other questions? Yeah, go ahead, Yannick.
Hi. So I've got a student working on also things with a time scale separations, and I don't fully understand what he's doing, but he's trying to find a relationship between, you know, the outcome of a dynamic and some differential equation, and you know, these things with I mean. It looked like, you know, the reason for the fact that these simple behavioral rules can be robust might be because you could have some underlying continuous time model of some kind of differential equation or inclusion. And then when you perturb it a little bit, you can use the stochastic approximation results to show that there is a relationship between the behavior of this discrete time system and the behavior of this underlying continuous time differential equation or inclusion. So I was wondering whether, you know, you had thought about this line of thoughts or this line of proofs of convergence, or whether, I mean, you just did not investigate that.
Sure, perfect. Yeah, this is a perfect question. In our two-time scale fictitious play, we have done something like this, where we have exactly like it, two different step sizes and decaying step sizes. On the other hand, here, local linear learning, you can think that there exists some step size, but that is a fixed unit fixed step size. Therefore, it will not form something like a recursion where the step size decays to 0. Right? Therefore, our proofs exactly inspired by those continuous time approximation results, but adapt them to this discrete time settings. We haven't been able to adopt this proof directly.
Okay, thank you.
Yeah, any further questions?
Also, maybe I would like to underline this. Maybe this can also be of independent interest, right? Where you cannot apply the classical stochastic approximation framework due to some unit step sizes. Or maybe imagine that one of them is Markov chain. The other one is some iteration with some decaying step size. Now, can you use some stochastic approximation for that case? Maybe that epoch-based approach can give some idea or solution concept to address that kind of problems as well, beyond just two different decaying step sizes. In it, we started to look at Benheim's work within that context, and they were very involved, right? I found some results related to the ergodicity property of non-homogeneous Markov chains. There are not many, but also they are very complex like they are not mathematically tractable as well, or they require very involved analysis. On the other hand, our coupling approach, I think relatively less involved to do the analysis.
Okay, if there are no further questions for now, let's thank Muhammad one more time. Thank you very much, Muhammad, for this
Thank you.
very interesting talk.
Thank you very much for the
Very
invitation.
nice.